Welcome to this video lesson series on electrical circuits, circuit analysis, and graphing. Now, the foundation of any section on physics is concepts, and the NSC have provided a beautiful document, a very comprehensive document that is titled the Examination Study Guidelines for Grade 12 for NSC. So this is where you will find the definitions that you will need to learn in order to answer the theory questions in NSC final exams. And if you are writing exams on circuit electricity in grade 11 or even in grade 10, you will need to know these concepts and be able to state these definitions. So let's start off with Ohm's law. So Ohm's law, there's various versions of Ohm's law, but in the NSC, the version that we want you to use is the following. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. Now, very often learners will get the first part of this definition correct. They will say the potential difference across a conductor is directly proportional to the current. Some may even switch it around and say that the current is directly proportional to the voltage, which is also not incorrect. But then they leave out this section here, at constant temperature. Now, they're going to lose a mark. And the reason for that is it needs to be stated at constant temperature because the resistance of that particular conductor needs to be constant if Ohm's law is going to hold true. You also need to know how to state the difference between ohmic conductors and non-ohmic conductors. So knowing this is very important. And basically, ohmic conductors are conductors when you plot V versus I, you will get a straight line, whereas non-ohmic conductors, you won't. So, for example, if I can just on the side here quickly show you. So an ohmic conductor, I'm going to use OC, an ohmic conductor, if you plot voltage versus current, you are going to find that as you increase the current, the voltage is going to increase directly proportionally. So this would be an ohmic conductor or an ohmic resistor. A non-ohmic conductor or resistor, there are various graphs for this. So, for instance, if you were looking at a voltage versus current graph, for instance, for a light bulb, you're going to find that it is initially going to look like it is an ohmic conductor, but soon it's going to deviate. You'll see it deviates there and starts to almost look like it's exponential or parabolic. And the reason for that is that the gradient of your voltage versus current graph is the resistance, because resistance is change in voltage over change in current, which is going to equal the gradient. Once it starts to become a curve, it's the gradient of the tangent, and that's going to increase as current increases because there's going to be an increase in the temperature because of the heating effect, and so the resistance is going to increase. So this is what a light bulb. And when we talk about a light bulb, we're not talking about an LED now, we're talking about an incandescent light bulb that is going to heat up over time. If, for instance, we take a diode, including a light-emitting diode, if I now plot I versus V, which would be what they call the characteristic, then what we find with diodes is that there isn't a current until you get to what they call the switch-on voltage. And then all of a sudden you get a massive conduction. So there you can clearly see that there is, this does not follow Ohm's law. So this would be a diode, and LEDs would be included in that because they're light-emitting diodes. If we were to plot the voltage versus current of a diode, then what we would find is, and I always find this one a little bit more difficult to draw, there would be the switch-on voltage, and then you would get this massive conduction. Now, looking at this, you'll see that it almost seems like there's an infinite resistance initially, and then once the voltage surpasses the switch-on voltage, you actually see that the gradient actually decreases, so the resistance decreases, and that's because of conduction across what they call the depletion zone in a diode, which goes past our syllabus. But these are examples of non-ohmic conductors. We're also going to need to know the definition of power, which is given here. So power is the rate at which work is done. We are given these formulae on the formula sheet, and we would need to work with these formulae when dealing with power. When it comes to other definitions that are really important, and that's really my focus here are the definitions, is that the definition of EMF is as follows. It's the maximum energy provided by a battery per unit charge passing through it. So in essence, it's the theoretical voltage of a battery. It's the ultimate or maximum voltage that a battery can supply based on the chemical energy stored in it. But as soon as current passes through it, there will be an internal resistance, and therefore there will be a loss of voltage. There will be an internal potential difference drop, which will then result in the operational voltage of the battery, the actual voltage being supplied to the external circuit, being less. So with having covered that, let's now move on to how we can do circuit analysis problems with problems that come from previous or past matric level NSC exam papers. So let's consider this question. So the battery in the circuit below has an EMF of 12 volts. Here we go. And an unknown internal resistance R. So if we look here, this is unknown. So we have the EMF. There's the EMF. Then it says the resistance of the connecting wires and the ammeter is negligible. So this is normally stated, and the reason for that is such that we can assume that the resistor, because the resistor of the ammeter is 0, that any volt drop across an ammeter is 0 volts. So we don't need to worry about an ammeter being a load that uses energy. The connecting wires, well, in practice, if one's looking at a very big electrical system, the connecting wires will definitely contribute to the overall resistance of the circuit. But in NSC school level circuits, we're going to assume that there's no volt drop across the wire. So when we're looking at, for instance, if we're looking at the volt drop across there, if we had to put a voltmeter in there, then the potential there and the potential there would be the same. So there would be no volt drop. So that would be 0 volts. So they always invariably put that in, should put that in. Now, it says that S is open. Write down the reading on voltmeter V1 and voltmeter V2. So if we look at V1, V1 is connected across the battery, and V2 is connected across resistor, the 6 ohm resistor. Now, there are different ways of approaching circuit analysis, and my approach is that it's one of a visual approach. Now, albeit that this circuit diagram is neat and beautiful, I don't believe that this circuit diagram actually facilitates you solving the problem in the best way possible. So I'm going to use something called the Rails method, the Rails format, and that involves redrawing the circuit in a way that it's going to be easier to interpret the voltage drops and the current splitting and really does help you with voltages. Now, yes, it will take you maybe 1, 2, maybe 3 minutes to redraw, but I'm of the belief that that is a valuable investment. So looking here, I'm going to redraw it, starting with the battery. So if you note here, what they've done here, if they have put the positive terminal at the bottom and the negative terminal at the top. Now, generally speaking, when we use Rails format, we do it the other way around. Now, it actually doesn't make a difference to the solution of the problem, because we tend to use conventional current. But in actual fact, in an electrical circuit like this, where your wiring is metal, the actual electricity is in the form of electrons moving from the negative terminal to the positive. So by me doing this, what I'm about to do is not wrong. So if I now go and I take the battery and I draw positive to the top and negative at the bottom, then the internal resistance, whether you put it above or below that symbol, doesn't actually make a difference. Right, we put a little dotted box around it. That denotes the battery. And I'm going to put that the EMF there is 12 volts. Remember, the EMF is the theoretical voltage. It's the maximum voltage, the maximum amount of energy that will be transferred to 1 coulomb of charge. So that would be 12 joules per coulomb, but that's an upper limit. That is a theoretical limit. That's when there's no current flowing. So what I'm going to do now, I'm going to go out there and I'm going to draw 2 rails. Now I'm going to use different colors. I'm going to use red for the positive rail. You don't have to do it in different colors. Right, and I'm going to use black for the negative or ground rail. So what I'm going to do here, and I'm going to spend quite a bit of time explaining how to redraw it into Rails format. You don't have to do it this way. So the current comes out and it goes through a resistor. Now, as soon as it goes through a resistor, the voltage is going to drop. So with the Rails format, what we do is we work with a positive transmission rail, which would be ideally 12 volts plus 12 volts, and then the negative rail, or the ground rail, which we are going to define as 0 volts, is going to be there. So that's going to be 0 volts, and ideally this would be plus 12 volts if voltage wasn't lost because of internal resistance. We are going to change this voltage just now, once the current starts flowing. Now, so we go out, and we see here that we encounter a resistor. So all resistances, all loads, get placed between the rails, between what we call the transmission rail. And by the way, this is the way they build electrical systems and circuits in the real world. There's a transmission rail, and then there is a ground rail. And between these 2 rails, there's a drop in voltage. And that's why we put the resistors between the rails. It requires us redrawing it. So we go through this resistor X. So there's resistor X. Okay. And then the current will then, at this point, the current will split. So that immediately tells us that the that part of the circuit's in parallel. So therefore what I do now is I go and I say, okay, so on the left we're going to have 6 ohms. So the current would go through there. The rest of the current would go through the 2,4 ohms and then through the 6 ohms. So on the other side, we're going to have 2,4 ohms, and we are going to have 6 ohms, and then they're going to join up here again. So if we look here, they're going to join up again, there at that point here, and then on the bottom rail, we are going to have the ammeter, this ammeter, and we're going to have the switch. So we have the ammeter here, and we're going to have a switch. I'm going to put that switch in. Sorry, I'm just going to put the switch in, and the switch is open at the moment. That is S. And then we arrive back at the battery. Now, in NSC, and IB for that matter, in South Africa, on school level, we assume that voltmeters have got infinite resistance. Now, there's no such thing as infinite resistance, but we assume that they have infinite or near infinite resistance. So we view a voltmeter as having an infinite resistance, which means that if we take the current and the volt drop across the voltmeter over the resistance, if this tends to infinity, then this is going to tend to 0. So what that means is we assume, because it has, the voltmeters have such huge resistances in comparison to the other resistors in the circuit, that the current is not going to flow through voltmeters. So the current will flow like this, it will flow like that, it will flow, as we've shown, it will flow like this. But when it comes to this point here, there's no current that flows through the voltmeter because it has a near infinite resistance. When we come back here, at this point, the current doesn't flow through there because it has a near infinite resistance. So the electricity comes, if the switch is closed, it will do this. So now, when it comes to the voltmeters, you can see here, we put the voltmeters in last. This voltmeter measures the voltage between that rail and that rail. So we can put V1 like this. We can say that V1 connects that rail to that rail. What is important here is that, and it's important when the switch is open, that V1 is connected on this side of the switch and not on that side of the switch. Because if it was on this side of the switch, then the voltmeter would not read anything when the switch is open. But because it's connected to the left of the switch on the side of the battery, it's going to read the EMF when the voltmeter, even when the switch is open. So now, that V1, we could also have connected like this. I could have connected it across like that, and it would still read the volt drop between the two rails. When it comes to V2, we can see that V2 is connected across the 6 ohm resistor. So when it comes to V2 is basically connected across the 6 ohm resistor, which means it's connected like that. But if you look between there and there, there's no volt drop because that conductor doesn't have a resistance. So the nice thing about the Rails format is that it really explicitly shows us, and it makes it very easy for us to see what the voltage is, the volt drop is across the different resistors. And whilst I'm doing this, I'm going to say, well, if we had to connect another voltmeter there, well, that would give us V parallel. So I'm spending a lot of time explaining the rails method. You'd obviously draw it much quicker once you've practiced this. So that's 0 volts. So that would be V parallel. Okay, we just want to make sure that that doesn't confuse you. And Vx, that voltmeter, would be like that. That voltage there, Vx, would be across resistor X. Now, what's nice about this is you can clearly see now visually that Vx plus V parallel should equal V1 when the switch is closed. And this is one of the nice things about the Rails format, is that it makes the visual input of the circuit into your brain through your eyes, I think, is more brain friendly than when it's like this. Because here, visually, it's not as explicit as to the fact that these two resistors are in series with each other, but in parallel with this. And that the volt drop across here plus the volt drop across there equals that volt drop. So that's why I like to use the Rails format when I teach circuit analysis. So now let's go, and we are going to use this as we solve this. So let's take a look at the reading on voltmeter V1 when S is open. Okay, so when S is open, V1 is going to read the EMF, which is going to be 12 volts. All right, how do we know that? Well, if you look here, V1 is measuring the volt drop across the battery when S is open, so there's no current flowing through it. So this little internal resistance here, which is unknown, no current will flow through it, so therefore there's no lost volts. So therefore the voltmeter will read the theoretical voltage of the battery. Now in practice, in order for it to do that, there needs to be a little leakage current that runs through. So in order for, if it's an analog voltmeter, for the little electric motor inside, which moves the coil's needle, there needs to be a little current in order to do that. But we're assuming, we're ignoring that leakage current. So we're assuming no current is flowing. This is just measuring the volt drop, the theoretical volt drop across the battery. V2, however, on the other side, is measuring nothing. There is no volt drop between there and there, because there's no current flowing through. So therefore, V2 is going to measure 0. So therefore, we can say V2 equals 0 volts. And so now we are going to move in to the next part, where they now close the switch and now a current flows. So now we are asked, what is the definition of power? Remember, power is the rate at which work is done or the rate at which energy is transferred. That is a standard definition. They tell us that the reading on the ammeter is 1,2 amperes, and the power dissipated in resistor X is 5,76 watts. Now, we do not know what the resistance of resistor X is at the moment, but we are going to use this ammeter reading and use the power in order to determine the power given in order to determine the resistance. So it says calculate the resistance of resistor X. So let's look at the ammeter, 1,2 amperes. So I'm going to go to my drawing. But now what we're going to do is we are going to close this switch. I'm going to close the switch, and by closing the switch, we're actually now going to complete the circuit. So now if the reading is 1,2 amperes on this ammeter here, that means that the current all the way along here, through here, is going to be 1,2 amperes. So if we had to have another ammeter here, it would also read 1,2 amperes. Now, at this point here, that 1,2 amperes is going to split into two separate currents, which are each going to flow in the separate parts of that parallel part of the circuit. But they will rejoin there, and then they will flow, it will flow at 1,2 amperes, again through the ammeter. Now, that means that the total current is 1,2 amperes, which means that the current flowing through X is 1,2 amperes. We haven't got the voltage across X, but what we do have is we are told that X operates at 5,76 watts. So X is operating, the power of X is 5,76 watts. And so that bit of information is going to help us to solve for X. So we can do that here, 8.3. We are now going to look at, we've got X, the resistance of X is unknown. We know that the power through X is 5,76 watts, and we know that the current through X is going to be 1,2 amperes. And so now we can find out what Rx is going to be. So referring to the power formulae that appear on your formula sheet, we have that power equals I squared R, or power is V squared over R, or power is I times V. Now, if we look at the first formula, we have the power through X, we have the current through X, and so therefore we can use this formula because there is only one unknown. So the power is 5,76 watts. We substitute that in, 5,76 watts equals the I squared, which is 1,2 ampere squared, times the resistance of X. Now, in NEC, we don't require of you that in the substitution step that you put the units in. Personally, I'm of the opinion that it's always good to be unit sensitive and put the units in, because it ensures that you have, it's a check, a double check, that you are using the correct quantity in the right form. But it's not necessary. So now we work out Rx. So Rx is going to be 5,76 watts, and we are going to divide both sides by 1,2 squared. So we've got 1,2 squared, and that's going to mean that Rx is, I'm just working it out on my calculator, 5,76 divided by 1,2 squared, and that gives us the value of Rx to be 4 ohms. So we can see this is the mark allocation is 3 marks, so I would assume that it would be 1 mark for the formula, 1 mark for the correct substitution, and 1 mark for the correct answer with the correct unit. So now that we've done that, my suggestion is that you go back to your diagram and that we actually put the 4 ohms in. Use the diagram as your platform for solving the problem using a visual approach. So we've got 4 ohms there now. And so if we wanted to, we could now work out the volt drop across the 4 ohms because we've got the current and we've got the resistance. So you see how nice it is that you've got your circuit diagram in this format, because visually it just stands out. It just makes the solution or the solving of the circuit so much easier. But then again, maybe I'm just biased to this particular method because I'm a visual learner. So let's now move on to the next problem. We are now asked to calculate the total external resistance of the circuit. So let's go back to our diagram. And if we look here, we're now looking at the external resistance. And here too, this is where the Rails format really does help us, because visually it clearly shows us the relationship between the resistors as concerns whether they are in series or parallel. So if we take a look at the flow of the current, the total current will go through the 4 ohm resistance. Then it's going to split, which means that these resistors will be in parallel with this resistor. But because this branch current that flows through this branch here does not split between the 2.4 and the 6 ohm, and it's certainly not going to go that route because this is a voltmeter with near infinite resistance, it's going to flow like that. These two are in series with each other. So we can then add the resistances, 2.4 ohms and 6 ohms. So we're going to do that. So we're going to say we're now working on 8.4. So we go here, we say, okay, so 8.4. When we look at the 2.4 and the 6 ohm, we can say that, let's call it R right. That's the right branch, is going to be 2.4 ohms plus 6 ohms, which gives us 8.4 ohms. Then if we look on the left-hand side, let's call that R left. R left is going to be 6 ohms. And these two branches are going to be in parallel with each other. So we are going to use the formula for parallel resistances. We can say that 1 over R parallel equals 1 over R right plus 1 over R left. So 1 over R parallel is going to equal 1 over 8,4 ohms plus 1 over R left, which is going to be 1 over 6 ohms. So therefore 1 over R parallel is going to equal, and we use the calculator, so we say 1 divided by 8.4 plus 1 divided by 6, and that is going to give us 2 over 7. Now, I like to carry this 1 over R parallel on the left-hand side here so that when I switch it, that I can clearly see that I have not worked out R parallel, I've worked out the reciprocal of R parallel. So now we need to reciprocate both the left and the right-hand side. So R parallel is going to be 7 over 2, which is going to give us that R parallel is 3.5 ohms. Now, one of the things I always like to do is to take the magnitude of the parallel resistance and then go and check that it is smaller than the smallest of the resistances in that part of the network or circuit. You can also use the term network for circuit. So if we look here, we can see that 3.5 is less than the 6 ohms, and 3.5 is certainly less than the 8.4 ohms. And the reason why the parallel resistance, the effective parallel resistance, and I use that old symbol that we used to use for resistances. So R parallel is 3.5 ohms. The reason for that is because of the fact that by adding resistors in parallel, we are creating extra conducting paths, which makes the flow of charge easier. So therefore, the effective resistance is less. So now we can see, once again visually, that the total current is going to flow through the 4 ohms and then effectively through a 3.5 ohm resistor before it reaches the ground rail. So 4 plus 3.5 is going to give us 7.5 because these two resistors are in series. So it's 4 plus 3.5, so we're going to do that. So we can explicitly, we're going to say that R external is going to equal the 4 ohms plus the 3.5 ohms, and that's going to give us that the total external resistance is going to be 7.5 ohms. Now, if we look at the mark allocation, that's 3 marks. So that would more than likely be 1 mark for adding the resistors together. 1 mark for this, but I always suggest that you put down the general formula first, just to play it safe, and then 1 mark for the parallel resistance. When it comes to 2 resistors in parallel, it is acceptable to use this formula. R parallel equals the product of the resistances in parallel, so it would be R right times R left over the sum of them, RR plus RL. But this is only allowed if you have 2 resistors in parallel. So that would be, you can see that R right is 8.4 ohms. And R left is 6 ohms, so we times by 6 ohms there, and we add by 6 ohms at the bottom. And so if we work that out, we get that 8.4 times 6 is going to give us 50.4 ohms squared on the top, and over 14.4 ohms, 8.4 plus 6 is 14.4. So if we divide by 14.4, then we get 3.5. And ohms goes into ohms squared, ohm times. So this is a quicker way, or an easier way of doing it. So now let's look at the next problem, and that is the reading on voltmeter 2. So now if we look at voltmeter 2 is the volt drop across the 6 ohm resistor. So V2 is the volt drop from there to there as the current flows through. Now, if we had the current flowing through this branch, then we could say that the V2 is the current flowing through this part of the branch times R, which is 6 ohms. That would be using Ohm's law. The problem is that we don't have the current at this stage, and we certainly don't have the voltage V2, because that's what we're looking for. So one of the ways of doing this is to, in actual fact, work out V parallel. And V parallel is basically the current, the total current flowing through R parallel. So I total times R parallel. So V parallel would be I total, which we have, times R parallel. And once we have that, we can then work out the current flowing through this branch, which would be V parallel, over the combined resistances, which is 8.4 ohms. And once we found that current, we can then work out V2. So we've got a plan of attack. So let's just look at what the mark allocation is. And voila, you can see that it is 5 marks. So this is going to require multiple calculations. So the first thing we're going to do is we're going to work out V parallel. We're going to do that here. So we're working on 8.5. I'm going to do it on the right here. So we look at 8.5. We're going to say, okay. So V parallel is going to be I total times R parallel. We have R parallel. And we have I total. I total is 1,2 amperes. So this is going to be 1,2 amperes. And R parallel we worked out as 3.5 ohms. I'm a great believer in actually solving this visually. You look at your diagram. That's why I've invested time in the diagram. I can see there's 1.2 amperes flowing through 3.5 ohms. So that's going to give us 1.2 times 3.5, and that's going to give us 4.2 volts. So V parallel is 4.2 volts, and I like to put it in there, 4.2 volts. Right? It's always good to take your answers and see that they fit in with the overall problem. If we look at the EMF, we see the EMF is 12 volts. We haven't worked out the operational voltage. We could, but with the lost volts, which we're probably going to do just now, we are going to have a voltage that is probably slightly less than 12 volts. So 4.2 volts would be considerably less than, let's say, for instance, it's 11 or 10.5 volts. So the actual value makes sense. Now that we have that, we have V parallel, we can now work out, let's call this I right. So this current here, we're going to call I right, because that's what we want. If you've got a diagram, it's okay if you add symbols, as long as you explicitly show it on your diagram is visible. So I right is going to be V parallel over R right. Now we've worked with R right, so I right is going to be V parallel, which is 4.2 volts. So we're going to work that out. So 4.2 volts divided by R right, which was 2.4 plus 6 is 8.4 ohms. So I right is going to be 4.2 divided by 8.4, and that gives us 0.5 ampere. Now once again, let's take a look at whether it fits in with the overall context. Well, the total current is 1.2 amperes. And we are saying that this is going to be 0.5 amperes. And so visually we can see, well, 1.2 amperes splits into 0.5 amperes, and I left would then have to be the difference, which is 0.7 amperes. Now, I believe that circuit electricity is one of those really challenging sections of physics, because it involves so many different concepts: current, voltage, resistance, and it also requires that we solve for these quantities in the context of something that requires us to deconstruct the circuit into different bits, into parallel part, and then within the parallel part, the right-hand side of the network and the left-hand side of the network, and then to synthesize. So it's important to always be looking at the relationship between things. So if this is 0.5 amperes, and this is 0.7, well, they add up to 1.2 amperes. But something else I want you to look at. Can you see that this is 8.4 ohms and this is 6 ohms? Well, the right-hand part of the network has got a bigger resistance, so you would expect it to draw a smaller current. And the left-hand side has got a smaller resistance, and you expect it to draw a bigger current. And it's exactly what it does. Also, if you times 0.7 by 6, I times R, you get 4.2 volts. So it's always good to just check that what you have solved actually makes sense contextually. So now that we have that the current is 0.5 amperes, we can now see, well, that current, that 0.5 amperes, flows through here. And so therefore V2 is 0.5 times 6 ohms. So we can say therefore V2 is going to be I right, the current through the right-hand branch of the parallel part of the circuit, times R. Now, if you're at a loss as to what to label, you can always take the actual value as long as it's unique. Well, in this case, it actually isn't. There's a 6 ohm there. But in the context of the right branch, I think you'll be okay if you say the resistance of the 6 ohms. And so therefore V2 is going to be 0.5 amperes times 6 ohms, and so V2 is going to be 3 volts. And so once again, let's just look that it makes sense. Well, if this is 4.2 volts, then this has got to be smaller, and we've worked it out to be 3 volts, so this is 3 volts. And the beauty about the Rails format is that it's very easy to see that this therefore would be 1.2 volts because of the fact that this voltage plus this voltage must be equal to this volt drop. And that's once again why I like the Rails format, because the voltages are the relationship of the voltages is explicitly shown. So now let's look at it's for 5 marks, so what would the mark allocation be? Well, I would think that there would be at least one formula mark, 4.2 volts. There would probably be a mark for substitution there, and maybe a mark there, or a mark here and there. So not 100% sure, but there would be 5 marks roughly like that. Now, if we now look at the next question, we see that they now change something in the circuit. So we're now going to move on to that.